afternoon, Year 10. We are looking at the respiratory system. Within that, in this lesson, we are going to be going over the composition of air, so what makes up the air that we breathe in and breathe out. And then we will also be looking at how gaseous exchange takes place. Before we start anything, we need to know exactly what the respiratory system does. So it has two pretty straightforward roles. The first thing that we need the respiratory system for is to bring oxygen in. That enables us to produce energy aerobically, so with the presence of oxygen. Now, the second thing that the respiratory system does is expels carbon dioxide. So that means that it removes carbon dioxide that we find in our muscles once we have exercised. There's two key terms that I want you to get down, or I need you to know. The first one is what inhaling is. Now, if I can get everyone just to take a really big deep breath in, that is inhaling. That's when we're breathing air in. And we can either call that inhaling or it's another process called inhalation. So if you're on the ball, you would have realised that the second key term I need you to know is exhaling. Now, that is very, very simply when we breathe out. And again, that process can either be called exhaling or exhalation. It's important we understand exactly what the air we breathe is made up of. So we're going to be looking at what the composition of inhaled air is and what the composition of exhaled air is. It's this common misconception that when we breathe in, we're only breathing in oxygen, and when we exhale, we're only exhaling carbon dioxide. So we're going to delve into this a little bit deeper. When we breathe in, so we take that big deep breath in, we are breathing in around 20% oxygen. We're breathing in trace of carbon dioxide, which means it's not quite enough for it to be measurable, but it is still there. And 79% of what we breathe is actually nitrogen. There will be a very, very small amount of water vapour whilst we're breathing in too. Now we're going to be looking at the composition of air that's exhaled. So when we take that big deep breath out, what is that air made up of? So there's actually 16% oxygen in the air that's exhaled, simply because our body can't utilise everything that we've inhaled. This is where we see another change. We exhale 4% carbon dioxide. If you think there's going to be a change in nitrogen, you are wrong. Our body can't actually use nitrogen. It's not a gas that does anything for us. So we exhale the same amount of nitrogen as what we inhale. Now, one of the changes, again, is that there is a larger amount of water vapour exhaled. Now, I want you to think of a time when you've breathed either against a mirror or a window and you get that mist that appears. That is the water vapour that's exiting our body. I want us to look at this slightly closer. So if I get this diagram up, we can see the one on the left-hand side is the air that's inhaled. So the carbon dioxide, the nitrogen here that is inhaled is the biggest percentage. So out of everything that we inhale the most nitrogen. Next, whilst we're inhaling, you can see that there is about 20% oxygen. There's a really, really tiny sliver here, and this part is the carbon dioxide. So here, like we said earlier on, there's trace. There's barely enough to measure it. Now, when we exhale our air, we can see that we've still got the same amount of nitrogen that's exhaling our bodies. Here, slightly less oxygen. Here, because obviously we've used that oxygen, that's what's oxygenated our muscles and allowed for aerobic respiration to take place. And then we've got a larger chunk of carbon dioxide exiting our bodies here. Whilst we're looking at this little chunk here, we know that there's more carbon dioxide that's being released because carbon dioxide is a byproduct of aerobic respiration. There's a couple of key terms I want us to be able to know before we move on, just so that we can really wrap our heads around these concepts. So firstly, I've got a picture on the screen at the moment, and I want you guys to think of a time you've gone to the doctors and you've been asked or tested for something like asthma. You would have been given one of these devices and you would have had to breathe into it as hard as you can. Now, if you are doing something like that, you will be measuring your vital capacity. This is the maximum volume of air that you can breathe out after breathing in as much as you physically possibly can. So think back to that time when you've been sat at the doctor's, you've had to take a really big deep breath in, and then you've exhaled everything out that you've got left in your lungs. That is your vital capacity. Now, the other key term that I want you to know about is your tidal volume. And this is really simple. This is how much I breathe in and out when I'm breathing normally. Now, these two terms are quite important when we're thinking about how our breathing is impacted when we exercise. So I want you to make sure that you've got those key terms down and you've learnt them so that we can work with them moving forwards. Now we've identified what tidal volume are and what vital capacity are, we're going to look at those in relation to being at rest and in relation to exercising. So whilst we're looking at our breathing volumes, there's a couple of bits that I want to highlight on this graph. So here we can see this person is resting. We know that because their lung volume is relatively low and it's pretty consistent, so we can see it's sitting at about 2.5 litres. At about 35 seconds here, we can see that this person's lung volume increases. Because it increases, we know that there is an increased breathing rate. There's an increased breathing rate as there's an indication that that person is doing exercise. We know this as their lung volume continues to increase over the period of about 60 seconds until it hits its peak here, where it's at about 5.1 litres. Whilst we're exercising, we know that we would see an increased tidal volume as the person that's exercising has an increased demand for oxygen. They have that demand for oxygen as their working muscles are working aerobically and they need oxygen. Or if they're working anaerobically, they need that oxygen to reduce that build-up of lactic acid. If we continue to look at this, we can see at around 115 seconds, so roughly here, the person stops exercising. We know that the person stops exercising around the 115 second mark because once they've taken their breath in, we can see that lung volume does not continue to rise up and it starts to level out. Where it's leveling out is where they are starting to be back at rest and their breathing rate is returning to normal. The key thing that I really want to emphasise here is the increase in tidal volume as our athlete or as our individual is exercising. We can see there is a real clear difference between their lung volume whilst they're at rest and whilst they are exercising. We can see the variation in terms of the graph going up and down because that's when the person is inhaling and exhaling. So we can see that very clearly on the graph. There's a couple of bits that I just want to go over before we finish looking at how exercise impacts our breathing. So one of the long-term effects of exercise is that we will see an increase in our tidal volume. So that means that our body will be able to utilise the air that we are using better and increase how much air we can take in each breath. So that means that our blood carrying capacity will increase. I don't want us to get confused with our vital capacity when we come to this, because our vital capacity, so the amount of oxygen or air that we can take in within one breath, will not increase depending on the amount of exercise that we do, because that comes down to how big or how small our lungs are. Now we've discussed how breathing occurs and we know why we need oxygen. Ultimately, it's to get oxygen to the working muscles and to remove carbon dioxide. But now what I really want us to look at is how does this differ for each athlete. So if I take my anaerobic athlete who's doing something like weightlifting, they need an increased breathing rate after exercise. The reason for this is because they need to repay their bodies with all of the oxygen that they've used to remove the byproduct of lactic acid. We're going to go into that in a little bit more detail later, so don't worry about that if you can't quite remember right now. It's not the end of the world. For our aerobic athlete, somebody that's like a marathon runner as an example, they have an increased breathing rate during exercise. The reason for that is because they have an increased demand of oxygen at the time that they are working. So my difference between the two athletes, my anaerobic performer, such as a weightlifter, they need extra oxygen after they have performed. I apologise now for my really poor handwriting on that photo. But my anaerobic athlete requires excess or an increased breathing rate after exercise. That's to repay all of the oxygen that they have used during anaerobic respiration. My aerobic athlete, such as my marathon runner, has an increased breathing rate during their performance as they have an increased demand for oxygen whilst they are performing. That simply means that their muscles require extra oxygen in order to work during respiration. Before we move on, I just want to have a really quick pause point. So we know that the respiratory system is used for inhaling and exhaling. We do both of those things so that we can take oxygen in and so that we can remove the waste product, which is carbon dioxide. We know that the air that we breathe in has a higher percentage of oxygen than what the air we breathe out. And we know that when we exhale, we are exhaling at a higher percentage of carbon dioxide. Tidal volume is the rate that we breathe as we are breathing normally. Vital capacity is the maximum amount of oxygen or the maximum amount of breath that we can take in one breath. Now we're going to move on to looking at what gaseous exchange is and how our breathing rate changes depending on which activity we will be doing. We are going to be looking at the whole process of gaseous exchange. So the process happens in two parts. One of the parts is the delivery of oxygenated blood to the working muscles, and the second part is the removal of carbon dioxide from the blood and turning that into a gas. So the first thing that I want us to look at is how deoxygenated blood is part of the process. So the first thing that's going to happen here is deoxygenated blood is travelling through the capillary. I'm going to use this little red arrow here to symbolise the carbon dioxide. As it arrives at the alveoli, the carbon dioxide is then going to diffuse through the very, very thin cell wall. I'm just going to draw a little squiggle here to symbolise that really thin cell wall. So our carbon dioxide will pass through this and it arrives in the alveoli. Once it's in the alveoli, it is now turned into a gas, so it can now leave the alveoli in the form of exhalation. So that's our breath that we release. The second part of the process is oxygen being inhaled. So remember, when we take that breath, part of the air that we breathe in is oxygenated. So now I've got oxygen sitting in my alveoli. I now need to get that oxygen diffused through the thin cell wall and into the red blood cells that are in the bloodstream. Once that gas has diffused through the thin cell wall, my blood can then be carried through the arteries to whichever relevant muscle needs that oxygen. Before we move on, I just want to touch very quickly on why we need gaseous exchange. Ultimately, gaseous exchange takes place so that we can take oxygen to the working muscles, and we can use oxygen either for aerobic respiration or for anaerobic respiration. The second reason why gaseous exchange takes place is because it allows us to remove carbon dioxide from the bloodstream and then exhale it out. A key word that I want all of us to get down and to understand is oxygen debt. Now, an oxygen debt is something that's built up in our bodies after we have done anaerobic activity. So let's say we have a sprinter. As an example, I've got Katarina Johnson-Thompson on here. She's just done her hurdles race. She sat down on the track and she's absolutely gasping for air. The reason why she's gasping for air, taking really, really quick, deep breaths, is because her body has just performed anaerobic respiration. All of her muscles have been working as quickly as they can, and they've now built up lactic acid. She's taken those really, really big, deep breaths to try and take as much oxygen into her body as possible so that her body can use that oxygen to break down the buildup of lactic acid in the muscles. Now, while we're on this subject, it's really, really important to notify and to note down that oxygen debt takes place after anaerobic activity. So we would normally see somebody in that state where they're breathing really, really heavily, really sharply after something like a sprint. We could say something like a long jump or a vault in gymnastics. It's after those really short explosive movements or phases of exercise have taken place.